In this video, we're going to discuss densities of Hausdorff measure, which describe the asymptotic behavior of Hausdorff measure on sets on small scales. Recall that the Lebesgue density theorem says that in RD, if we look at the ratio of the d-dimensional measure of a set inside a ball with the d-dimensional measure of that ball, then this converges to 1 for almost every x in the set A and 0 almost everywhere outside the set A. Also recall that the Hausdorff measure of a ball in RD is equivalent to the diameter of that ball to the power d. So this result says that almost everywhere the measure of a set A inside a ball is asymptotically just like a constant times r to the d on small scales. So a natural question then is, does a similar phenomenon occur for general sets? So that is, for an s-dimensional set of finite s-dimensional measure, do we have that its measure also looks like r to the power s in balls of small radius? So the answer is a very strong no, and this even fails for integer dimensions, as we'll see. First, let's formulate some terminology and notation to describe the polynomial-like asymptotic behavior of measures on small scales. So for a set A and a non-negative number s, we first define the upper density of A at a point x to be the lim sup of the ratio between the Hausdorff measure of A inside the ball Bxr divided by that ball's diameter to the power s. We similarly define the lower density as just the lim infimum of the same quantity. And finally, we define the s-dimensional density to be the limit of this ratio if the limit exists. What we can establish in general is that upper densities are reasonably behaved. So given a set A of finite s-dimensional measure, the upper densities lie between 2 to the minus s and 1. Moreover, for an hs measurable set A of finite s-dimensional measure, we have that the upper densities are equal to 0 for hs almost every x outside the set A. And finally, if we have a measurable subset B of A, then the upper densities and also the lower densities of these two sets agree almost everywhere in the set B. So we won't prove these results here, but the proofs should seem familiar to the techniques and arguments that we used when we were studying derivatives of measures early in the course. So all in all, we see here that there is some behavior similar to the Lebesgue density theorem, but only when we consider upper densities. Even though the upper density is always positive, the lower density can actually be 0 everywhere along a set of positive and finite measure. So we're just going to sketch an example in the plane of dimension s equal to 1. So our set is going to be constructed as an intersection of compact sets E sub k as follows. So first of all, we're going to define our first set E sub 0 to be the unit square in the plane. Okay, now inductively, if given a set E sub k that is a union of dyadic squares, we take each dyadic square q and we replace it with 2 to the k squares of size 2 to the minus k L of q. And we space these squares as far as we can from each other inside the square q. So it turns out that we can space these squares apart by distance at least approximately 2 to the minus k times the side length of q, L of q. Okay, and then as I said earlier, the resulting, our desired set is going to be the intersection of all these sets Ek. Now, notice that we can define a Frostman measure so that the measure of each square is equal to the side length of, each square in the construction is equal to the side length of that square. By the construction, we can see that the measure of any square is going to equal the sum of the measures of the next generation of squares contained in that one. So it's not hard to show that this definition results in a measure whose support is equal to our set E, and it turns out that it's going to be a Frostman measure of dimension 1. So all in all, this construction will give us a set of positive and finite measure. In fact, the measure of our set inside each one of these squares will have measure comparable to the side length of that square. Okay. Now, in this first picture here, so I've drawn a square q. So imagine this is some square q inside our construction. And I've replaced them with 2 to the power 5 2 to the power 4 many squares of side length 2 to the minus 4. Okay, and notice that if I zoom in on a portion of one of these squares and blow it up to this picture, what I see is that the squares that I've introduced inside Q, they're each spaced apart by at least 1, 2, 3 many squares of the same side length from their neighboring squares. Okay. Now, for each one of these blue squares, so let's say I take this square here and I blow it up to this picture here. So now what I've done in each one of these squares in the construction is that I've replaced it now with 2 to the 5 many squares, each of which have side length 2 to the minus 5. And again, I've spaced them apart as much as I can. And in particular, if I zoom in around, a wide box around one of these squares, what I'll see is that this square is spaced apart from all the other blue squares by distance equal to 1, 2, 3, 4, 5, 6, 7 many squares of the same side length. Okay. Now, recall that the measure inside each of these blue squares is comparable to, or the Hausdorff measure of the set E inside each one of these blue squares is comparable to the side length of the square. But if the distance between these squares and all the other neighboring squares is increasing, this means that if I look at a ball centered on this square whose radius is equal to this distance to the other squares, I see that the ratio of the mass of E in this ball in comparison to the diameter of this ball is shrinking as I zoom in. So you'll notice here, so I've drawn this ball whose radius is going to be equal to 1, 2, 3 times the side length of this cube. And then now I draw another ball centered on this square whose side length is equal to 7 times the length of this square. And you notice that the square is taking up less and less space inside this ball. So that means that the ratio of the measure of this blue square divided by the diameter of this ball is going to be shrinking as I zoom in on smaller and smaller balls centered on my set E. And in fact, for any point in E, I can find a sequence of radii going to 0 so that these ratios of the measure of my set inside this ball divided by its diameter goes to 0 everywhere. So we've seen that the density of Hausdorff measure need not exist. And in fact, the lower and upper densities can actually be very far from each other. So what can we say about a set if the upper and lower densities do agree with each other? That is, what can we say about a set if the densities do exist almost everywhere? So this is where things start to get a little bit interesting. So first of all, if you have a set where the s-dimensional densities exist almost everywhere, then it turns out that s must actually be an integer. Not only that, if we zoom in on almost every point of this set, the set begins to resemble an s-dimensional plane on small scales. Finally, if we're looking at one-dimensional sets and the lower density happens to be strictly bigger than 3/4 almost everywhere, then that actually forces the density to exist and equal 1 almost everywhere. So in other words, it's impossible to have a set whose densities hover in the range between 3/4 and 1. The lower density either has to be at most 3/4 or it must equal 1. And in fact, there is the famous Besekovich 1/2 conjecture that says that we should be able to replace 3/4 with 1/2. In order to discuss the first two results, we're going to need to introduce a whole new set of techniques for studying geometry of measures called tangent measures, which will be the focus of the next 2 weeks.